Good morning, welcome to this tutorial, basic tutorial for visual TCL form finding. We are going to introduce the software and to present some basic features to let you understand more or less the concept of the software and to use it and process the example files. First of all, you can download the software in www.wikilista.com visual TCL form finding. There you have a basic web page with some description of the software, some YouTube videos or some files, and here you can download the software, so you can use it in your computer. Some other files, some other YouTube videos, and at the bottom of the page you have some input files you can use in the software. So the web page, I'm going to update every news of the software there. You can also find some information in LinkedIn. So there we go. The software doesn't need installation, just download the software and zip it, and then just run this bat file and you will have the main window of the software. The first thing to do is you have, well, the software is partially in Spanish and partially in English, but is some basic information. So you have geometry in file, and fichero salida is the output file. The extension is FFI for finding input, FFO for form finding output. In the output you have the result of the form finding process, and the input is the input file. Both files have the same format, so you can use the output as an input as well, so you can continue with the form finding process. If we go to explore, I have two examples here. We are going to go for the bridge example. That is simpler and is quicker to calculate. We open, and then with load the form finding input, we load the file. We can enlarge the window, and the first thing it happens after you load the file is a summary of the system, where number of nodes, number of elements, number of geometric fixations you have. At the bottom of this summary you have two numbers, this number and this number. They have to be the same number to be able to solve the system. So as more geometric constraint you introduce in the file, in the input file, you will increase the this number, and when they are even, it means that the system is solvable. So there you have to solve the system, to save the output file, to export, because we can export the information, the result, to several software, and the graphic screen. If we go for graphic screen, you can see the 3D geometry of the input file. So at the bottom here you have to plot the fixations. Redraw is to redraw these fixations, So to redraw the geometry, and because we have enabled the fixations, now you have all fixations. With control and just going over the different entities, you can see that here in this part of the window you have some information. So here is a nodal fix, that is number of the node and Fy, and is this node and x fixation in x direction. If you enable nodal loads, is to plot. Here you have the scale of the different entities. With nodal load, if you go to redraw, is the, remember, with control and going over the entity, you have the information, is telling the node and the load in that node we are introducing in the input file. Here is another number of equilibrium, another node equilibrium, and node forces. There are other options. I think if I go here, redraw, yes, with the right button of the mouse and dragging, you create a window zoom, and these two loads, nodal loads, let me see if I can go here. These are loads that the system are solving to simulate the bottom of the arch fixation. Because it's moving, you cannot restrain this node. This node is free in X and Y. So remember, right button of the mouse and dragging, you have the window zoom. So you have at the bottom of the arch, you have a vertical fixation, but horizontally is free. So I'm introducing two loads in X and Y, and these loads are not given loads, are loads calculated by the software. And they will be the amount of load that the software will calculate there to find the equilibrium of that point. So with some all extension, you come back here. I'm reducing the scale, redraw, so they are smaller. In this part of the window, I have default views, so X direction, Y direction, Z direction, and some other isometric views. It's not theoretically isometric, but from the different corners. So in this way, you have the control of the geometry of the visualization. With the left mouse of the bottom of the mouse, you have a dynamic view, so you can change it to whatever direction. You have the chance to plot the original geometry, that in this case is exactly the same because I haven't solved the software, the file. Quads, you can plot the quads if you have in the file. In this example I don't have quads, but quads are to introduce surface loads, number of nodes, so you have all node numbering, and number of elements, you have all the information there. So with editor is to edit. You have the input file. Soon I'm going to go through it and explain the different parts of the file, but basically you can edit this file, and Then you have the solve button. We are going to solve this geometry. Some information here at the bottom of the main window is the maximum number of iterations you want to go, maximum displacement per iteration, maximum change of load in each iteration, maximum tolerance to stop the calculation. A group divider is to divide in groups the different elements. So if we solve the software, we have two state bars. One is going through each iteration, displaying the different stages of each iteration, and the main one is telling you the number of iteration is going through. Here we can see 14th iteration, 15th. Is pretty quick. I'm going to remove these loads because they are going quite large, as they are the reaction of the arch. And when you have 0, 0, that is maximum displacement 0, 0, and maximum forces out of equilibrium 0, 0, it means that you have reached the solution. You were able to see that after each iteration the geometry is updated, so you can get a feeling if the software is working or not, if it is converging. So this is the equilibrium found for this structure, and you can see that you have a gradient of color depending on the forces of the elements. In red you have compression, in blue you have tension. Going with control and over the element is telling you element number, from which node to which node, load conditions, the starting conditions, the final load is 4 meganewtons, 4.969 meganewtons, and the length of the member. In this example, I have forced the solution for all these elements to have the same length. So if you go here, is 4.754. If I go to another element, is 4.754. So all these elements have the same length. At some point that length is changing, so if we change the view, you can see I go here, is same length than this element, same length as this element, but this element I think is half of that or something like that, but this element has the same length and this the same length. So you can see that the software is quite powerful because you can control exactly the geometry of the structure, at the same time it's solving the equilibrium. Once you have the system solved, the first thing to do is to choose the output file. By default it goes to FormFinding outputs. I have already saved that, but I'm going to replace it, and pressing save FormFinding output, it has saved the result of this FormFinding. With edit you have the output file is exactly the same format of the input file, so you can use the output file as an input and continue the analysis. But all the coordinates of the nodes, for example, now are updated to the equilibrium solution. At the same time, all the elements has exactly the equilibrium load. So Here you have fixation, relative length fixation, fixation in length, in total length, relative length between nodes, to fix node, the plane of the node, so you can force the node to move in one plane. Nodal force, these are the reaction nodal force. You can see here that you can name the different elements or entities of this input file, not only with numbers, also with letters. So you have the output file is a complete input file, but with all the information updated to the equilibrium solution. Once you have saved that, you can export it. To export, the first thing you have to do is to eval the model. So the software goes through all the elements, and depending on the group divider, it's creating the different groups here. The software has detected two groups. Group 1 are the cables, and group 2 are the arches. This is automatically done because I have already introduced that information in the software. If we go to the input file here, in export group divider, I have specified the same thing as group divider, because you can have one group for one group divider for processing all the information, and the export group divider for exporting in the case you need different thing. And then export params, I'm telling that group 1 has I don't remember the first information now. The second one is cross section, the color to print to plot this element in the finite element software. Then if it is a cable or if it is a beam, and because I have introduced this information in the input file, when I eval the model, I have this information already updated. So I remember. Here you can activate or deactivate the group if you want to export it. Here you choose the color, just clicking in the box. Then is the group of this the group it will have in the finite element software, the number of cross section, and then if it is a cable, a truss, or a beam. Once you have this solved, this already configured, depending if you are working with symmetric model or not, you can specify if you want to create the symmetric solution as well. So symmetric in XZ plane and symmetric in YZ. In this example we don't have a symmetric solution, so we don't enable this. This you can leave by default, and once you have specified this parameter, you can generate the export model. So in the memory of the computer we have already the model export, and then I have for strand 7, for sophistic, DXF, and ANSYS. The first thing to do is, for example, for DXF is to specify the name of the file. I have already saved that, but I'm going to overwrite it and export the ACAD file. And then I will go for sophistic, for example, again, name of the file, and save sophistic file. Once I have exported, I have finished the work, so we can go for this file and open it with the different software and see how it looks like. In the export directory folder, we have the bridge DXF. Double click, open in AutoCAD, and you will see that the software, when it's exporting, is assuming some cross-section depending if it is a beam or a truss or a cable. So the DXF file will have a layer with 3D elements, and it's geometry that is already. So if we go for a zoom to this area, for example, you can see the arches with 3D shape and the cables. I'm going to change the view style, so you have a complete 3D and with a very approximate cross-section depending on the loads of the element. So the software is assuming the maximum absolute load for the entire group and is giving that cross-section to the complete group. So DXF is already there. You have some layers in the file, 3D group 1, 3D group 2, and then you have the line representation. So if I hide the 3D shape, you have the line representation of that structure, so you will be able to process it if you need it with different software. So DXF is working, and now we are going to go for the DAT file, sophistic DAT file. And you can see that the software is creating a fully functional file for sophistic with the aqua module with different materials for steel and cables and the different cross sections. You can run this module, fully functional, and then you have the Sophie MHA with the geometry. The only thing is that this geometry, to be able to calculate it, to run the analysis, you will have to change the fixation of the bottom of the arch, because in the form finding software was only vertical with 2 virtual loads to create equilibrium, and now you will have to detect these nodes and put a full restraint node. Well, you can see that is working geometry, and then Sophie load that is introducing the pre-stress in the complete structure, and then the module ASE, advanced solver engine, to solve the equilibrium, and there we go. Almost all the job is done. Form finding is simple, is quick, and the export is also fully implemented, so you can run analysis as soon as you get the result from the form finding. This is the end of this tutorial, and